Okay, so next we are going to start the second section of this chapter. Local maxima, local minima and their relationship with derivatives. Now, before starting the section, let us recall something, namely the definition of maxima and minima of a function. And we came across that definition in the previous chapter. It's in fact this definition. Definition 965. So in this definition we have a function, a real valued function with domain x, where of course x is a subset of the real numbers itself, and there is a point x naught in the domain. We say that f attains maximum at x naught if maximum at x naught if f of x naught is greater than or equal to f of x for all x in x. Similarly, we say that f attains minimum at x naught if f of x naught is less than or equal to f of x for all x in x. The exact opposite inequality. Now, instead of having this notion which works for the entire domain, we can see a local version of it. In a small region, we can try to find maximum and minimum if they exist. And that's how the section starts. So this is the definition of local maxima and local minima. And the beginning is saying we still have a function whose a real valued function whose domain is again a set of real numbers, and we have a point x naught in the domain. We say that if attains a local maximum, respectively a local minimum, that is actually the second part of the definition, but here itself we will state it. If there exists a positive real number delta such that the restriction of f to this set has a maximum, respectively minimum at x naught. Okay, so instead of concentrating on the entire domain x, we are concentrating on a small region around the point x naught. And that small region is determined by this delta. Delta in this sense can be thought of as a small positive real number. However, in mathematics, the word small by itself does not have any definite meaning. Delta can be anything, but usually it's taken small so that we can avoid some parts of the original domain. Note, however, that in order for the function to be meaningful, for the restriction to be meaningful, we take the intersection of the domain of the domain of f, which is x, and this small region around x naught. Let me just give you an idea of how this is different from this notion. Although you can, of course, see how it is different, but still, let me give you not an actual example. We are going to see one example, but even before that, let us see how these two things are not the same. You just imagine a function whose graph, say, looks like this. Say this is the graph of the function. Okay, and just for the sake of definiteness, let us assume that the function is defined not on the entire real line, but on this closed interval. This closed interval. So this point is A and this point is B. So the function actually is a function of this type. Now you can see that the function actually does have a maximum, an ordinary maximum at this point. Here. This is the ordinary maximum value. Okay, so that value is, say, something, say y1 suppose, and that value is attained at the point, say this point x1, and the function also has a minimum value, an ordinary minimum, which is this value. This value, say this value is y2, which according to this diagram is negative. Maybe it may be negative, it may be positive also if the graph lies above the x-axis entirely, and this value is attained at the left boundary point A. However, there are other values also. For example, you can see that here there is a value. This value y3 has been attained at this point, and that point is, say, x2. Now y3 is actually not the maximum value of f, because that is y1, which clearly is greater than y3. But y3, in spite of not being the maximum, is a local maximum. Why? That's because if you concentrate your attention around x2 in a small enough region, for example, you choose that region to be, say, this. Okay, so that this left vertical line is x2 minus delta. and this right vertical line is x2 plus delta. You do understand what delta is. Delta is this length, so that if you go to the right of x2 by that length, you reach x2 plus delta. Subtract delta from x2, you reach this left boundary point. Boundary of what? Boundary of this open interval. And this is that open interval. Here, of course, we have x0, but that's just a name, right? Within this region, if you concentrate your attention, you then see that within this small region, this is the maximum value, because elsewhere the values are smaller than y3. That is why this is a local maximum. This value y3 is a local maximum value, and that value has been attained at the point x2. There is a local minimum value also, similarly, at this point. This value, and that value you can call it, say, y4, which is a local minimum value, because just like this local maximum, you can find a small region around this point at which that y4 is attained. So you can call this x3. Around x3, if you choose a small region by choosing a small enough delta, within that region, this is the minimum possible value, the smallest value. Note also that this local maximum value is actually smaller than the global maximum value. Similarly, this local minimum value is greater than the global minimum value. Okay, so that is the idea. Now let us see this next item, which is an example which basically illustrates this same thing. And in this example, of course, we are going to consider a concrete function f with its own formula, everything. You can try to understand this even better by considering these values as scores, okay, score value of some team. So there will be, in any sport, okay, there will be some value which is the absolute maximum, which has been scored by some team all across the globe. I mean, it's something international. However, if there is a national championship or something like that, which has been organized, and there a score has been reached, which is not the global score, it's not as good as the global score, but still locally it is the highest. Like that, you can try to understand this. Oh, well, before the example, there is a remark, however. What this remark says is that so the remark is just about calling this a global maximum and calling this value a global minimum in order to distinguish them from their local versions. That's because in that definition from the previous chapter, where we have defined maximum and minimum value, we did not use the word global. Now, however, because we have a local version, so we may as well call these values global. Note one more thing, that a global maximum is automatically also a local maximum. And in this case, any delta works. you do not have the fear in, you see, if you are choosing this delta large enough so that within that region x1 also comes, then the maximum nature of y3 is violated because there is a larger value, and that's why you normally choose a small enough delta so that other potentially larger maximum values can be avoided. However, you do not have that fear here. If you have a global maximum value attained at some point, then any delta you choose, you have the definition of local maximum at that point. Okay, so automatically a global maximum is also a local maximum. Similarly, a global minimum is also a local minimum. That's what this remark says basically. So let us now see example. Consider the function f from R into R given by f of x equal to x square minus x to the power 4. So here that domain x is the entire set of real numbers itself. Alright. Now this function does not have a global minimum, or more specifically at the point 0 the function does not attain a global minimum. If does not attain a global minimum at x equal to 0. In fact, there is no global minimum. Let me just draw the rough shape of the graph of this function. Although the graph is not there in the text, but it's just a matter of drawing. You can see how the graph looks if you use a graphing facility, or if you want you can plot points and try to see it for yourself also. The graph roughly looks like this. X-axis, y-axis, this is your 0, and let us also locate say 1 and minus 1. Okay, and it goes like this. I mean, it comes up like this, and the shape is roughly like this. You can see why that happens. When you put, say, this is minus 1, this is 1. If you put x equal to minus 1, you are getting 0. If you put x equal to 1, then also you are getting 0. And if you put x equal to 0, then also you are getting 0. Which is why the graph touches the x-axis, crosses the x-axis. Here it itself, I mean, at the point 0, you can say that it does not cross the x-axis, but it touches the x-axis. At these 3 points, okay, and it just goes down like this without any bound, as your x either goes to the left or to the right. And that is why the function does not have a global minimum, because there is no minimum value. Also keep in mind that the domain is the entire set of real numbers. So you can go to the left side as far as you want, also to the right side as far as you want. The more you go, the smaller the values become. In particular, at 0 there is no global minimum. And in fact, that can be demonstrated simply by considering this. This is because f of 2, for example, is 2 square minus 2 to the power 4, that is 4 minus 16, which is minus 12, that is less than 0, and 0 is f of 0. So smaller than f of 0 also there are values, and f of 2 is one such value. But if definitely from the graph itself you can see f attains a local minimum at x equal to 0. And instead of simply relying on the graph to justify this, the author has given a simple argument also. By choosing, alright, so in order to prove that the function has a local minimum at 0, we need to first of all choose a delta. Now if you choose delta equal to 1, we get the open interval minus 1 comma 1, which is just 0 minus delta comma 0 plus delta. That means this open interval. Now what happens in this open interval? Also, let us keep in mind, let's just be absolutely clear about everything. We are not, whenever we choose such a delta neighborhood of x naught, we don't really simply concentrate on the open interval itself, but its intersection with the domain of the function. In this case, however, the domain is the largest possible set. So the intersection is this itself. Okay, now when x belongs to this region, after writing when, should not write then, we have this, okay, the absolute value of x is less than 1. So if you take square on both sides, you get x square less than 1. And hence, now if you multiply on both sides by x square, the inequality does not change direction, it does not get reversed, because x square is positive. No, x square is non-negative, x square may be 0 also. That is why instead of simply writing less than, we need to take into account that possibility that you may have 0 also. In that case, you will have equality. But anyway, you do get this inequality. So, what is the consequence of this? The consequence is this: f of x equal to this. Because of this inequality, this is greater than or equal to 0. And 0 of course is f of 0 for all x belonging to minus 1 comma 1. Not for all real numbers x, but for all x in this interval. And that's how f attains a local minimum at 0, because elsewhere the f values within this interval are more than 0. Now next comes another example which is a little peculiar. A general advice while studying real analysis and also while studying calculus is that whenever you encounter a function, always see how its graph looks. Okay, that can really change things, change the way you look at things. I mean, if you just simply see the text and go through the calculation and everything, you will see, okay, everything is okay. But you won't really understand what's going on until you see the graph. So if graph drawing is possible, nowadays it's very easy. There are online graphing facilities like Desmos graphing calculator, for example. You just write the equation, even if it is an inequality, it will immediately give you the region or the graph, whatever it is. Now let's see the next one. Okay, this time consider the function so the rule for the function is that of the identity function. However, it's of course not the identity function because the domain and range are different. You can say it's the inclusion function, but let's not go into those terms here. The thing simply here is that the domain is the set of all integers. The range of course is R, and f does not change anything. Okay, if you give an input to f, it gives that input back as output. Okay. Now what about the maximum, minimum values of this function, global as well as local? Clearly, f has no global maximum and no global minimum. Why? That's because the values of f are all the integers, and there is no smallest integer, there is no largest integer. So no global minimum, no global maximum. But local minimum and maxima exist. However, f has a local maximum and a local minimum at every point. That means every integer. How is that possible? It sounds extremely strange. However, it is possible due to the discrete nature of the domain Z. And again, instead of simply writing arguments, I am going to first of all draw a figure. There is no need to draw both the axes, okay? We just need to see one thing. That will make everything clear. So this is my x-axis, and of course this small x. The entire x-axis is not the domain, only the integers. And say the integers are present here, like this. So what we are saying is that the function has a local maximum as well as a local minimum at every integer. Let us just arbitrarily choose any integer, say 1. Okay. How do I prove that the function has a local maximum at 1, for example? That means I have to choose a delta. Now, as delta, say I choose 1 over 2. That I can choose because it's a positive real number. Then, what is this interval? 1 minus 1 over 2, comma 1 plus 1 over 2. It is this open interval. The boundary points are the midpoints. For example, this boundary point is the midpoint of 0 and 1, which is this 1 minus 1 over 2. And that is just 1 over 2. And this is the midpoint of 1 and 2, which is 1.5 or 3 over 2. Alright. Now, so that means what interval am I getting? I am getting this interval. Now let me take its intersection with the domain of the function. The domain is the set of integers. Within this interval, what are the integers? Only one integer, that is 1. Okay. Now, what does it mean? It means that if I consider this restriction, I can write z first, it does not matter. Intersection is commutative. This restriction attains a maximum and attains a minimum. Note, however, that this restriction in fact has just one value, which is f of 1, and that in fact is equal to 1. So obviously that value itself is maximum. Maximum of what? Maximum of this restriction, not the entire f. And that value is also the minimum of this restriction. And that's how f attains a local maximum and a local minimum at x equal to 1. And that maximum as well as the minimum local value is also 1. So you see how strange it is. The original function has no global maximum, no global minimum, but has the local versions of maxima and minima at every point of its domain. Okay, so that is this fourth item. All right. Now comes a result. What happens if a function attains a local maximum or a local minimum at a point where it is also differentiable? All these results we are already familiar with from calculus. This is proposition Oh, I have written proposition 6. The example, however, is item number 4. So there is a 5, something I have missed here. Okay, I will see what it is afterwards. It's not, I don't think it's a very, it will most likely be a remark or some example. It won't be a result. So let us just continue like this. Local extrema are stationary. Extrema is the plural of extremum, which means either minimum or maximum. Okay. Now, here the statement is this. Suppose A and B are real numbers such that A is less than B. Let f be a function from the open interval a comma b into R. Also let f be differentiable at some point x naught in a comma b. Now, if f attains a local maximum or a local minimum at x naught, local max or local min at x naught, then the derivative of f at x naught is equal to 0. Okay, that's what we mean by stationary. So you see the hypothesis. First of all, we are talking about an open interval, and that too a non-degenerate open interval, an open interval which has things in it. That's why we need a to be less than b. And we have our function whose domain is this open interval. And there is a point x naught in the open interval at which two things happen. F is differentiable, that is the first thing. And the second thing is that f attains a local maximum or a local minimum at that point. Then the derivative of f at that point has to be equal to 0. We are of course not going to prove this now itself. All the proofs are going to be done in the exercises. And this is the first exercise. For the proof, see exercise 10.2.1. All right, and now some discussion about what will happen if we drop this hypothesis. Why do we need differentiability? Well, of course, we need differentiability. Otherwise, how can we say something about the derivative if the derivative does not exist at all? But we also have open interval. What would happen if we do not take open interval, for example? So let us, instead of writing down these things, let me just talk about the actual example itself. You consider this function. Okay, and we of course also know how its graph looks. Let me also draw the graph. So this is our 1, this is 2, and the graph is that line segment with both of its endpoints included in the graph. Besides this domain being a closed interval, is everything else about the hypothesis true in this case? Yes, because the function is differentiable at every point, in fact, inside this interval. F prime of x exists for all x belonging to this interval. Oh, and in this regard, let me also say at this point that we do not really have to bother about the fact that there are boundary points at which also we are saying that f is differentiable. Because of the way we have defined the derivative of a differentiable function, we can do it anywhere in the domain, provided that the point where we are defining differentiability is a point in the domain and is also a limit point of the domain, both of which are true for both of these endpoints. So we need not bother about whether the point at which we are talking about differentiability is or is not an endpoint. It may be an endpoint. Okay, so this exists for all x, and in fact this is equal to 1 because after all it's just the identity function. So you see that this conclusion is not true in this case, and that has happened because we have allowed a closed interval instead of an open interval. And at the same time, if we do not have the hypothesis of differentiability, I don't really understand how we can even talk about this if we do not assume differentiability. However, something goes on in that case, and for that we have to see the second exercise. We will see this at the time of going through the exercises. And there is another aspect of this result. Its converse is not true. Converse is false. For that, see the third exercise. Now, if one combines this proposition with the maximum principle from the previous chapter, you remember the maximum principle? It says that if there is a real valued function defined on a closed bounded interval like this, and such that the function is continuous throughout its domain, then the function has a global maximum and a global minimum at some points inside the domain. That result. If one combines that result with this proposition, one then gets the well-known Rolle's theorem. That is the next result. So this will be seventh item. The statement of Rolle's theorem is this: let A and B be real numbers such that A is less than B. Let F, this time however, we are going to consider a closed interval. Be a function such that for some reason the author has used G here instead of F, but it does not matter, of course. You can name the function using any letter, such that three conditions are true. The first condition is that F is continuous on its domain. Okay. Number two, F is differentiable on the interior of the domain, that means the open interval. And there is a third condition also. F of A is equal to F of B. At the boundary points of its domain, F has the same value. Then F prime of x is equal to 0 for some x belonging to the open interval a comma b. You also probably already know the geometric significance of this theorem. It says that if you have a function like this and you draw the graph of the function, then in this open interval at some point the graph will be horizontal, and by that I mean that the tangent to the graph at that point will be horizontal, and that is why the slope of the tangent, because this is the slope of the tangent at the point x comma f of x actually, that is 0. Okay, and its proof also will be seen in the exercises. See the fourth exercise. And there is a remark also after this. The remark says that we have of course considered differentiability of the open interval, but you may have a function f which is differentiable on the closed interval itself. For that also, if the other things are true, I mean if this is true in particular, then Rolle's theorem is applicable. That's because differentiability on the closed interval automatically implies continuity also on the closed interval. Here, however, note carefully that differentiability on the open interval implies continuity on the open interval, but does not necessarily imply continuity at the boundary points also. That's why we have to state both these hypotheses. It's not that you can get Rolle's theorem simply by stating hypothesis 2 and 3, because one needs to be stated separately. So that is this remark. And finally, Rolle's theorem has a very important corollary, which is the well-known mean value theorem. The statement of mean value theorem starts just like this, but the mean value theorem does not assume this hypothesis, and accordingly its conclusion is also different. So again, not going to write everything though. A and B are two real numbers of this type, and f is a function like before, such that number 1, f is continuous on the closed interval, and number 2, f is differentiable on the open interval, and that's it. We are not assuming this. Then the derivative of f at x is equal to f of b minus f of a divided by b minus a for some x belonging to the open interval. Now, after stating Rolle's theorem and mean value theorem, if I do not draw diagrams, then it's really a bad thing. What do these theorems tell us geometrically? It tells us that there is no need to draw the y-axis, but still, just for the sake of it, I am drawing the y-axis. So this is my interval a comma b. So the mean value theorem says that f is continuous on a comma b, okay, which means that the graph of f in this of course here itself there will be the graph. On this side and this side there is no graph, because this is the domain of f. The graph is in one piece, it's not broken. That's what we mean by continuity. And by differentiability, we mean that the graph does not have sharp corners, sharp ends like this. It's smooth, okay. And that's it. So let me just draw such a graph. Say f of a is this, okay, and f of b is this, and the graph goes like this then. you of course understand that f of a may be positive, f of b may be negative, both may be positive, both may be negative, all possibilities are there. One of them is this. Alright, now looking at this quantity, what do you recall from coordinate geometry? Is this point not the point a comma f of a? This point, and this point is the point b comma f of b. If you join them by a straight line like this, then this ratio is the slope of this straight line. What the mean value theorem is claiming is that this slope is equal to the slope of the tangent to this graph at some point. In other words, there will be a tangent to this graph that will be having the same slope as this. That is, that will be parallel to this secant line. And there are multiple points like that. One of them is this. This is a tangent to the graph at this point, which is parallel to this secant line. There is another one also. This one. And in fact, there is another one also. But at least one will be there. That's what the mean value theorem is claiming. There are 3 points at which the tangents are all parallel to the secant. Now, what happens if one also includes this condition, that f of a is equal to f of b? In that case, these 2 points will be at the same level, wherever that level is, so that the secant line is horizontal, so its slope is 0. So the tangent also has to be horizontal, which is why its slope also is 0. Okay. Actually, the Rolle's theorem should be a corollary of mean value theorem. However, the mean value theorem is derived as a consequence of Rolle's theorem. That's why it is being called a corollary. However, this is where the section ends. And after this, we have the exercises which we will do next week. So that's just it for tonight. So see you in the next video, next community post, whatever that is. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.